Sugam Prabha. Digital India. Educated India.
Hello students. In this lecture, I will discuss a wave equation for finite string. In the previous lecture, I set up the structure of the wave equation for finite string and give you a homework to go beyond that. I hope that some of you get success in that. So today, I will finish this finite string and show you the full solution. After that, I will go to heat equation. For finite string. So this is the wave equation. Psi t, that means del square psi, del t square equal to 1 by c square psi xx. Okay. Finite string, that means x belongs to 0 to L. Okay. That means string is of length L. And t greater or equal to 0. That means t starts from initial time t equal to 0 to t equal to infinity, long future. There will be BC at both ends, as a boundary now, because the string is tied at both ends. Okay, and you pluck it, small disturbance, and there will be a wave there. It's called stationary wave. After getting solution, I will discuss the interpretation of the solution. So psi 0t equal to psi lt equal to 0. There will be IC, initial condition, which is psi x0 equal to fx, psi t x0 equal to gx. Okay. You know, because of this initial condition and boundary condition, it is called initial boundary value problem, IBVP. Right? Let us label it as 1A. This is 1B, BC, 1C, IC. So that we can refer to as problem 1. Now we will do solution. So we will use, of course, method of separation. That means we will take the solution psi xt, which we have to find as a separable from, that means as a product of capital X, which is function of x only, and capital T, which is function of t only. Let us put that. Let us label this equation as equation 2. Now you know you have to substitute. You have to substitute solution 2 into wave equation 1A, so that you will get two eigenvalue equation. You know that. After putting, you will get x double dash by capital X equal to capital Y double dash by C square, sorry, should be T double dash. So, okay, should be T double dash by C square T. Both sides must be separately constant. So I am taking the separation constant as this form. Always I advise that to take separation constant square form. Negative sign is just for convenience. Repeatedly I told when I started this method of separation that at this juncture you do not know what are the allowed values of k. You do not know whether k is real or complex. Okay. So when we will go, we will use first boundary condition, then we will get the eigenvalues, and eigenvalues are labeled by k. So let me label it as 3 and now go to next page. So as I told you that separately check whether the separation constant k equal to 0 is allowed or not. That means check first whether 0 is one eigenvalue or not. Then separately, after checking, if you find that yes, it is included, fine. Then consider k not equal to 0 case and investigate, find all the values. If you find k not equal to 0, then fine, then 0 is not the eigenvalue. So separately consider. Then you see that here k equal to 0 will give you capital X is simply a linear function of this, no, it should be small x, okay, linear function of x. Then if you apply boundary condition, both end it should be 0. So you will get a equal to b equal to 0. That means capital X equal to 0. Okay. It is not allowed because eigenvector must be non-zero. So therefore, you conclude here that yes, k not equal to 0. But still you do not know whether k is real or not, real, maybe complex. We do not, we have to find it. So consider now k not equal to 0 case. And in previous page, you see, you have this equation, x double dash equal to minus k square x and t double dash equal to minus k square c square capital T. Both are simple equation. Only thing is that this is eigenvalue equation. K is unknown. Okay, so actually capital X and capital T will be eigenvector corresponding to value of k, specific value of k. So we will label it as xk suffix tk. Okay. So xkx equal to, I am taking, there will be two arbitrary constant, of course. I am taking this symbol C1, comma k. So in suffix I am leveling k, okay, because it is kth arbitrary constant times cos kx plus C2k sin kx, right? Similarly, you will get tkt, same type solution. We will use different, let's say level it as d1k cos ckt, okay, plus d2k sin ckt. So let me level this equation. We level it up to 3, no, in previous page. So let's say it is 4, it is 5. Naturally now I will use boundary condition. And boundary condition is psi vanishes at both it. So first let us apply it on 4. So use BC, boundary condition. What we will get? If you put x equal to 0 on right side of 4, essentially second term will vanish and first term will be constant. Because left side is 0, of course that means you are getting C1k will be 0. Okay. So that means this eigenvector will contain only sign term. C2k sin kx. So what I am using here? What I have used here? Using psi psi 0t equal to 0. Okay. So we have another boundary condition. So which is psi lt equal to 0. So if you put that here, so you will see that now you cannot say C2k equal to 0 because then x, capital X will be 0. It is not allowed, eigenvector must be non-zero. That means sign part must be 0 at x is equal to L. So you have from here sin KL equal to 0. That means you get eigenvalues, which is because KL equal to n pi, right? Right? And that means your eigenvalue you can write k, you can label it as kn, okay, which is n pi by L, where n, range of n cannot be 0, okay, so it should be 1, 2, 3, so this gives you, equation 6 gives you all sets of eigenvalues. You now know k is real, which is n pi by L. So that means we get capital XK. There is an arbitrary constant there, I know. And these arbitrary constants will be evaluated using initial condition. But before that, we have to find this one as usual, as we do for this. So I'm going in next page. So there is a tk, which is cos ct. So what we can do that first let me write psi. This is psi, remember? Product of this So we find the form of capital X and capital T. Both contains arbitrary constant. Capital X contains one arbitrary constant. Capital T contains two arbitrary constants. Since it is product, so that means actually there are two arbitrary constants because C1k in capital X can be renamed as C1k into D1k is AN. Similarly, C1k into D2k equal to BN. So it was equation 2. So what I am writing here, from 2 psi xt can be written as summation. Why summation? This is from the, we can write here, principle of superposition that I discussed before. Over all k, you have to take a summation. Since k is taking discrete values, and it is leveling at n, so n is going from 1 to infinity, summation. And then there will be a factor here, sine n pi x by L. That means, you see, here there was, this is, if you understand this one, argument was kx, and k is now n pi by L, okay? So it is now sine n pi x by L, and then you have capital AN cos n pi c by LT. We put k, so there will be no k now. N pi c by L times t, okay, plus Bn sine n pi c by L times t. What is the level of this equation? Okay, let's see. We were up to 6. So let me label it as equation 7. Note that here AN actually renamed as previous arbitrary constant C, what was that? C1k or C2k? C2k. So C1k was 0. So C2k into D1k. D1k, and Bn is C2k times D2k. So actually we have two arbitrary constants which we have to find. Then actually equation 7 gives us solution. To get these two family of arbitrary constant, we will use, there are two initial conditions. Remember, psi x0 equal to fx and psi t x0 equal to gx. So we have to calculate psi t also. So from 7, differentiate partially with respect to t. So psi t xt will be, you see, n pi c by L. This term will come out, right? So your psi t will be summation n equal to 1 to infinity. And remember that our solution is always smooth. So the series, this infinite series, is term by term differentiable, term by term integrable. Okay, so we can do that. So n pi c by L sine n pi x by L times minus an naturally is it will be sine n pi c by lt, okay, plus bn cos n pi c by lt. Let me label it as 8. Use now use initial condition to get these two family of arbitrary constants an, bn. Okay, I will do that on next page. First is psi x0 equal to fx. Okay, implies, you see psi x0 is here, equation 7. So if you put t equal to 0, then cos term will be 1 and sine term will vanish. So only an will remain, right or not? So it will be from 7, you will get fx equal to summation n equal to 1 to infinity an sine n pi x by l. Let me label it as 9. Now in the previous class I introduced and discussed the results of Fourier series. So you must recognize here that 9 is Fourier sine series, right? So by Fourier inversion theorem, you actually know this n, an. An is, there will be 2 by L factor because it is defined only integral 0 to L. So you have to make an extension minus L to 0 and then you have to make an identical copy to apply this theorem, right or not? So you will have this 2 by L and integral 0 to L f x prime, okay, sine n pi x prime by L dx prime, where you know n ranging from 1, 2, 3, so it is equation 10. So you get already an. X prime is used as a dummy integral value. Okay. Okay. So now use second one. Second one is psi t x0 equal to gx. So this time from 8, equation 8, showing you again, going to previous page, you see this is your equation 8. So here if you put t equal to 0, now an vanishes, an term first term, and bn will remain, cos term will be 1. So only bn will be there, right or not? So that here you are getting for psi t x0 gx equal to, right, summation n equal to 1 to infinity n pi c, this is a full constant, n pi c by L times bn, okay, sine n pi x by L. So this is also Fourier sine series. So that means you can write But remember, there is a factor n pi c by L here. So full things equal to, so I am taking it in the right side. Okay. So Bn equal to 2 by n pi c. Okay. Integral 0 to L gx prime. Okay. X prime is just integral variable, dummy integral variable. That's why we are using. You can use u. Same thing. Gx prime sine n pi x prime by L dx prime. N is, 1, 2, 3, so on. So this completes the solution, because you see, I'm going back to previous page. This is your solution, equation 7. Only thing is that contained two families of arbitrary constants, a and b. But now a and b are known by 10 and 11. So you have a solution. If you wish, you can plug a and b into 7. It will be a longer equation containing these integral forms. Okay, this completes the solution. Now, I am giving you a problem. I will not solve. You have to solve. You can do that. If you listen these video clips repeatedly, you will understand. I will give you this solution for your exercise. Along with, I will write down the solution in the next page. Okay. So take this exercise. Suppose a string is tightly end suppose a string is tightly tied, okay, at both ends. Let's say at x is equal to 0 and 2. If the string is released from rest, okay, if the string is released from rest with a initial profile fx equal to sine cube pi x by 2, if this, find the solution psi xt, find the solution psi xt of transverse vibration at any point x, where x is of course 0 to 2, at any instant t greater 0, assume 2 meter per second is wave speed, and all quantities are in ms units. Okay, do that. I will just write down the solution, answer actually. Answer is psi xt equal to 3/4 sine pi x by 2 cos pi t minus 1/4 sine 3 pi x by 2 cos 3 pi t. This is the solution. Okay. Now, as I told you, before going to heat equation, briefly, I will give you a interpretation of Fourier series solution, which we obtained. Interpretation of Fourier series solution. The solution we obtain sometimes called interpretation of Fourier series solution. So how to do that? You see, what we will do, to give an interpretation, we don't need to exact expression of A and B. Okay. So what we will do here, I am showing you in this page where there is this psi is where? This one, equation 7. Okay. So in equation 7, what we will do, there are two terms here under summation. First term is with n sine into cos. This I will name it as psi 1. Okay, level by n. And there are second term which is sine n pi x by l into sine n pi c by l t. That we will label it as psi n2. So there are two parts. Each part actually represents stationary waves. Each part. Okay. I will show you that there will be a phase difference of the two components, psi n1 and psi n2. Okay, phase difference of pi by 2. So there will be a mixture of waves. Okay. So let me go to the current page. So write psi xt in this equal to summation n equal to 1 to infinity an by 2 psi n1 plus bn by 2 psi n2. Okay. Now, psi n1, why I am taking this half factor? Because there is sine cos. So I will use it as a 2 sine a cos b formula, trigonometry formula. So I will write it as in this form. This will give you an interesting things. You will recall the characteristic direction that that reminds you. If you see the form, it will be sine term n pi by L times x plus c. Okay. Plus sine n pi by L x minus c. Similarly, psi n2 will be cos n pi by L x minus c minus cos n pi by L x plus c. So you see, psi n1 is a function of x plus ct, psi n2 is a function of x minus ct. So remember the dilemma solution I discussed in the previously in some clip, that along characteristic direction is x plus ct and x minus ct. So solution must be function of this. Only thing is that in that case, which was infinite string and semi-infinite string, it was any function, right? Which depends on initial condition and so. But this time you will see it will be only sinusoidal. Okay. So if I level it, let's see. It was okay, equation 11. So let me level it as equation 12a, 12b, 12c. If we analyze only 12b, it is sufficient. You will understand. So first of all, note 12b represents sinusoidal waves of amplitude an by 2, because an by 2 is the prefactor of psi n1. Okay, this is first thing. Not only this, it is moving towards not only an by 2, there is, so let me write down in this way. 12a, not 12b. I am writing generally full two terms, so it is 1. So it is 12a. 12a represents sinusoidal waves of amplitude an by 2 and bn by 2. One is moving towards left, another is moving towards right. So moving towards left or right, Okay, with speed c, with speed c. This is one. Another point is that, let me go to next page. How to tell this? Phase of psi n2 differs from, just looking into the equation, this can be pointed out. Okay, that's what I am doing here. Phase of psi n2 differs from that of psi n1 by pi by 2. This is called phase shift. In language of wave, this is called phase shift. Okay, this is called phase shift. Okay. Now, you see there is a n ranges from 1, 2, 3, 4, so on. So summation, sum of many terms. So we will now examine each term for n equal to 1, 2, 3. So examine for n equal to 1, 2, 3, so on. So for each value of n, it is called nth mode wave. Okay. So what we want to examine? We want to examine how many times nth wave crosses, okay, how many times nth wave crosses equilibrium position. Equilibrium position means naturally horizontal axis. This we want to check. Now you see, if you look into psi n1, let me go back to previous page. Psi n1 is sine plus sine, okay? So when it will be 0, because it crosses horizontal axis, at that point it is 0, right or no? So when it will be 0, you see psi n1, that means nth wave, xmt, xmt, that means x is equal to xn, equal to 0 for xm equal to m by n times L, where m is allowed to take only 0, 1, 2 up to n, where of course n you know 1, 2, 3, so on. So to understand from here, you see, first of all, why m is allowed to take only these values, only up to n plus 1, because wave can't go beyond x is equal to 0 and x is equal to L. It is tied at both ends, right? So you see, for m equal to 0, it is the leftmost point, and m equal to n, it is the rightmost point. So there are only allowed values of n plus 1. So from here you understand that we can say nth mode wave, it is called mode. So let me use this wave language. So nth mode wave has n plus 1 nodes. One addition, n plus 1 nodes. Nodes means, node means the point at which solution crosses x-axis. Okay. So in the next page, just let me draw a sketch. Okay. Let me use black ink. Draw a sketch. So this is our axis. This is tied at both ends. And this is the equilibrium position when you did not give any disturbance to the string. Now you give a disturbance. So for n equal to 1, okay, in its first wave, it will have only 2 nodes at x is equal to 0 and 1, because when n equal to 0, you see, n equal to 0 means m equal to 0 and 1, 2 nodes. So it will be simply this. Now n equal to 1, you will have 3 nodes, right? N plus 1, 0, starting from 0 to n. So 0, 1 minute, n equal to 0 is wrong. I am very sorry. This is wrong. Because n is not 0, n is starting from 1. So this figure is for this. N equal to 1. This is n equal to 1. Now n equal to 2. This is m equal to 0, 1, 2. So that means there is an intermediate crossing there. So that means you have this way this time. Okay. This is n equal to 1. This is n equal to 2, right? So if you go now increasing n, you see n equal to 3, m is 0, 1, 2, 3. So it has 2 nodes. That means it will be one. Yes, it will be this type. So this is n equal to 3. So if you go now n equal to 4, it will be m equal to 0, 1, 2, 3, 4. So there will be 3 nodes now. So naturally more vibration. So in this way, you will see that finally higher increasing you will be have vibration. This is called stationary waves. Okay. So this is in contrast with the wave equation solution of wave equation I have obtained, and I have given you that interpretation that time. You remember that was progressive wave because ends were free, so that was moving. But this case, this is stationary waves. Okay, some more terminology perhaps good idea to discuss. One is wave number. Wave number is denoted by k equal to n pi by l. Wave number is actually number of waves per unit distance. Number of waves per unit distance. This is called wave number. And what more? Length of full cycle. Length of full cycle. This is denoted by lambda. Okay, so actually full cycle means prime cycle, what I mean. Otherwise, there will be an n term. So lambda equal to twice pi by k. Frequency of wave. These are all terminology relating with wave language. So frequency of wave omega equal to ck. Periodic time denoted by capital T, which is 2 pi by omega. Okay, which is the time lapse between two same phases. This is called periodic. Okay, and another point is that this is a last remark, that if an observer is stationed, okay, at a fixed point, x, then exactly one full cycle passes her after time t. So this completes the discussion of wave equation. Now, in the next page, I will today give because there is I think sometimes remains 5-10 minutes. So I will just give an introduction to my next topic, heat equation. It will be elaborately taken up in the next lecture. So in heat equation, first of all, I want to use Laplacian operator del square first. Laplacian operator is denoted as del square, sometimes called nebula operator. Okay. Now, in 2D, Cartesian coordinates, del square will be del square del x square plus del square del y square. Essentially, in 3D Cartesian, del square will have one more term, del square del x square plus del square del y square plus del square del z square. Similarly, we can write down 2D polar coordinate, 3D polar coordinate. I will give you later when I will go to discuss Laplace equation, the last topic of this course. So this is why I want to, I have written down this, because you see, all equation can be written down, this wave equation, heat equation can be written down in terms of this del square operator. Like wave equation has del square psi wave equation has some problem to write down in this way. We can write down like del square psi equal to 1 by c square del square psi del t square. So then you see what we did here. For one dimensional, naturally del square has actually only one term. That's why we taken these things. So now you understand that if you have to write down 2D or 3D wave equation, you can write down. Of course, in this course, solution will not be discussed, but at least form you understand. That's the reason why I introduce here del square. Similarly, heat equation can be write down like del psi del t equal to alpha. Alpha is some heat constant, positive, like C was there, which was wave speed there. So del psi del t equal to alpha del square psi. So you see, when you go to one dimensional, it will be simply del psi del t equal to alpha del square psi del x. And actually in the next class, we will consider only 1D heat equation. So let me finish today just to write Laplace equation. Laplace equation now I will not write explicitly. I will just write Laplace equation is very simple. Del square psi equal to 0. There is no time variable here. So naturally, in the next in the class when I will discuss Laplace equation, I will write down explicitly this thing. So that's completes today's discussion. We finished wave equation for finite string in this class, and previous clips I discussed infinite string and semi-infinite string. So in the next class, I will start one-dimensional heat equation, and elaborately I discuss how to find the solution with relation to different types of boundary conditions. Okay.